Hi, good day to all of you. So our topic for today is Pearson's product moment correlation coefficient, or what is simply known as Pearson's R. So unlike the other statistics that we already discussed in class, which focuses on identifying difference between and among groups, Pearson's R is designed to calculate or measure the relationship between two variables, or the extent to which two sets of data vary together. I think the keyword here is strength, because Pearson's R measures how strong the relationship is between two variables. Okay? Now, there are several things that we have to know about Pearson's R before we actually proceed to the computation. First is that it is symmetric. What do we mean when we say symmetric? To illustrate that, I have a sample set of data here. These are the number of hours a student spent studying and his or her corresponding exam score. Actually, the R observed of this set of data is 0.91. That indicates a positive correlation, which means that the number of hours a student spent studying is positively correlated to his or her exam score. In the same manner, his or her exam score is positively correlated to the number of hours a student spent studying. So that is what we mean when we say symmetric. The correlation between X and Y is the same as the correlation between Y and X. Clear? Now, the second thing that we have to know about Pearson's R is that correlation does not indicate causation. What does that mean? To illustrate that, we have a sample research from Turner. She did the research on the type of shoe and the oral skills of her students. She wanted to know if there is a relationship between these two variables. Interesting, right? And the results were there is actually a positive correlation between these two variables. Students who wore a particular type of shoe had better oral skills than other students who wore other type of shoe. Now, what do we mean when we say correlation does not indicate causation? It means that this variable, the type of shoe, is not necessarily the cause of the student's oral skills. Yes, they have a correlation, but there is no cause and effect relationship. Similarly, buying a particular type of shoe would not increase your English skills. So that is what we mean when we say correlation does not indicate causation. One variable is not necessarily the cause of another variable. Clear? Okay. Now, let's proceed to the correlation value. What we have to remember about correlation value is that it can only range from -1 to +1. No more, no less. It cannot be 1.2, it cannot be -2. Only from -1 to +1. We can see from this number line that +1 means we have a perfectly positive correlation, and -1 means we have a perfectly negative correlation, and 0 means we have no association between the variables. Now, what do we mean when we say there's a positive correlation, there's a negative correlation? That brings us to the three types of correlation. We have positive, negative, and no correlation at all. When we say positive, or let's say our variables are A and B, we have variables A and B. Positive correlation means that as the values in variable A increases, the values in variable B also increases. They have a positive correlation. Now, if we have a negative correlation, that means that as values in variable A increases, the values in variable B decreases. Okay? And if there's no correlation between the variables, we cannot actually say what is the relationship between the two variables. The change in values of one set does not affect the values of the other. Okay? Now, to fully understand the features of correlation coefficient, the succeeding slides would show us different correlation values and their corresponding scatter plot. So we would know how each set of data looks like when placed on a two-dimensional graph. Okay? So our first value here is r equals positive 1. If you remember our number line a while ago, positive 1 indicates a perfect positive correlation. So if you would look at our data here, as the values in variable A increases, the values in variable B also increases, resulting to a straight line that climbs uphill. Okay? Question: do the values always have to be the same to achieve this? To have a perfect positive correlation like this 1, 1, 2, 2, 3, 3? The answer is no. Okay? And the second set of value, we also have r equals positive 1, meaning we also have a perfect positive correlation. But if you're going to look at our data here, still, as the values in variable C increases, the values in variable D also increases, but the values are not the same. So this set of data here also gives us a line that climbs uphill for a perfect positive correlation. Okay? Now, for our third set of data, we have r equals negative 1.0, and this means that we have a perfect negative correlation. If we're going to look at our data, as the values in variable E increases, the values in variable F decreases. So if we're going to plot it in a scatter plot, it would give us a straight line, but this time it goes downhill. Okay? For our fourth set of data, we have r equals 0.28. This is near 0 already. So, if you would look at our data, we could not identify a relationship between the variables. Plotting it would just give us a collection of rather isolated dots. There. There's no relationship between the variables. Okay? For our fifth set of data, we have r equals 0.85. If we're going to look at our values here, as the values in variable I increases, the values in variable J also increases. And if we're going to look at the scatter plot, we can see that all the dots are near the line. Okay, because this is giving us a moderately strong positive correlation. Okay? Now, let us proceed to the assumptions for Pearson's R, or the conditions that we have to meet in using Pearson's R. The first assumption is that the independent and dependent variables are measured on an interval scale. If you can remember, we have three scales: the nominal, the ordinal, and the interval. And it is interval which give the most information about variable levels, okay? Because it tells us not only the category and the order, but it also tells us that the intervals between the ordered categories are equidistant. And that idea of equidistance is what gives the interval scale its mathematical properties. That's why we can use it for Pearson's R. For example, if we have a test scores as our variable, for example, we have 10 item tests, we have 11 possible scores, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And all those scores have equal distance from each other. They have equal intervals. Okay, that's what we mean when we say equidistant. On the other hand, if our scale is ordinal, this is the statistic that we could use. The second assumption, since this is a parametric statistic, is that each of the two variables is normally distributed in the population and the sample of participants. The third assumption is that each observation is independent from all others. The first aspect of this assumption tells us that the collection of data in the independent and dependent variable must be entirely distinct from one another, okay? The second aspect tells us that there should be no collaboration among the participants. The researcher must ensure that the participants are working independently. Okay? The fourth assumption is that the relationship between the two variables is linear, not wave-like. Okay? And this could be verified by using a scatter plot. So we could know if there is a linear relationship between the two variables. Now, let us proceed to using Pearson's R in the 10 steps in statistical logic. We have a sample study here, so let me read it. The director of an organization that supports foreign language summer camps for native English-speaking children wanted to conduct a study on the potential usefulness of a foreign language aptitude test for identifying children who would be most likely to be successful in the intensive summer camp program. To do so, he needed to know how strong the relationship is between performance on the aptitude test and success in foreign language learning in the summer camp environment through a final test after the camp. From all of the children with no exposure to Spanish who registered at one camp to study beginning Spanish, he randomly selected 15. Take note of that. He randomly selected 15. During the first day of orientation for the summer camp, the 15 children took the aptitude test. At the end of the camp, all of the students took the final test, a test of their Spanish ability. He collected the final test scores of these 15 children so he could determine whether the relationship between the children's performance on the aptitude test and their level of communicative language ability was strong enough to be considered statistically significant. So based on this study, we could see that our variables are the results of the aptitude test and the outcome of the language ability test, which was given after the camp. Okay. So, step 1 is to state the formal research hypothesis. We have two, the null and the alternative. So, our null hypothesis is there is no statistically significant correlation between language aptitude and language learning as measured by the final test. And since there is enough evidence to say that there is a positive correlation between the two variables, the aptitude test and the final test, our alternative hypothesis goes like this. There is a statistically significant positive correlation between language aptitude and language learning as measured by the final test. Okay? Step 2 is to set the alpha. Since this is an exploratory research, we set the alpha to 0.05. Okay? For step 3, we have to select the appropriate statistic for analysis of data. If you can remember our study a while ago, the researcher wanted to know the relationship between the two variables, the aptitude test and the final test. Therefore, a correlation statistic would be appropriate. Now, to know if Pearson's R is the best statistic, let us check the other assumptions. Second, he randomly selected the participants and the tests he chose are designed to yield normally distributed data. Yes, the researcher randomly selected 15 children from all the participants and the tests he used are designed to yield normally distributed data. So yes, we adhere to this. Next, the aptitude test and the final test are entirely distinct from one another, meaning no items from the aptitude test would appear on the final test or vice versa. And it was ensured that the participants worked independently, there was no collaboration, and no cheating among the participants, okay? And a scatter plot will be made to guarantee that the relationship between the two variables is linear. You would see the scatter plot later in step 5. Step 4 is to collect the data. So this is our data from Turner's book. We have 15 students and these are their scores for the aptitude test, and these are their scores for the final test. Okay. For step 5, we have to verify that the assumptions for the statistic are met. So let us check. First, the independent and dependent variables are measured on an interval scale. And yes, the study adheres to this because the scores obtained by the participants on the aptitude test and the final test measure things exactly. We have 1 point per correct item, making it equidistant and therefore has mathematical properties to be used for our Pearson's R for our analysis of data. Next, the data for each of the two variables are normally distributed in the population from which the participants were randomly drawn and in the two groups. As mentioned a while ago, the researcher randomly selected 15 participants from all the camp participants. And the aptitude test and the final test are norm reference, meaning they are designed to yield a normal distribution. This could further be checked using the SPSS. The third assumption is that each pair of observations is independent. Okay, so none of the items from the aptitude test would appear on the final test, meaning they are entirely distinct from one another. And it was ensured that all participants work independently on the test. There was no collaboration and there was no cheating among the participants. The fourth assumption is that the relationship between the two variables is linear. So this is the scatter plot I'm talking about a while ago. We can see that the variables have a linear relationship. Okay. Now, for step 6, we have to calculate the observed value of our statistic. Okay, but before we actually continue on the actual calculation, it is advisable that we prepare a table first, just like this, so that computation would be easier later on. We would just fill in the data, okay? So I have prepared a whiteboard here, yes. Okay, so what we have to do is to just fill in this table. We have to look back at our collected data a while ago. So let me just copy it. This would be our X and this would be our variable Y. X is the language aptitude and Y is the results of the language learning test. So let me put in here students 1, 2, 3, 4, 5. X score of student 1 is 29 and 39, 33, 39, 25, 36, 30, 38, 33, 46. Okay? So what we have to do next for the next column is to just square the value here. Since we're asking for x squared. So 29 squared. Let me use a calculator. 29 squared is 841. 841. For y squared, just have to multiply this value with itself. 39 times 39. The answer is 1521. 1521. And for the last column, xy, we just have to multiply the value here with the value in this column. So 29 times 39 gives us 29 times 39 equals 1131. 1131. Okay? So we just have to continue that process with the other data. So after completing it, okay, you have to put the summation of each column. For So you put in here the summation of x, or the sum of all the values in x, all the values in y, summation of x squared, summation of y squared, summation of xy. Okay? And if we're going to continue this would be the result. Ta-da! Okay? Are we correct? 841, 152, 111. Yes. So this is the final table. As I was saying a while ago, you put a summation here, summation of x, summation of y, and so on. Okay? Now, here is the formula for Pearson's R. N is 15, right? We have 15 participants. Multiplied by the summation of xy minus, you multiply this first, summation of x multiplied by the summation of y. Okay, before you subtract the product here, over the square root of n, 15, summation of x squared minus, you square it first before you minus it, there. Okay. Now, you fill in the values from the chart, from our table, and add the information for n. Okay, so this is the result. We just fill it in, and 15, summation of xy minus summation of x multiplied by here, summation of y. Okay, and you do the calculations. The result is, after doing the calculation, the result is 0.71, and that indicates a moderately strong relationship. Now, please remember this value. This is our R observed, because we will be using it later on step 8, okay? For another sample on how to compute for the Pearson's R, you may consult this video. I believe you have a copy of this PowerPoint presentation. It is in our class email. So just click this link and it will bring you to another sample computation, okay, for Pearson's R. Now, we have a value already, right? 0.71. The question is, how do we know if we are going to reject or accept our null hypothesis, and if that value is strong enough to be considered statistically significant? That brings us to the rest of the steps. Step 7. What we would be needing in this step are this information. We need the degree of freedom. The formula is very easy. Just n minus 2. Since we have 15 participants, right? Minus 2, the answer is 13. So that is our degree of freedom. 13. Second information that we need is the alpha. Our alpha is 0.05. And the third information that we need is a table for critical values. I already attach a link here. You have to click it and it will bring you to a table for critical values for Pearson's R. This is what you're going to see, okay, if you're going to click that link. Okay, since our alpha is 0.05 and our degree of freedom, this is for the degree of freedom, is 13. Let's look. So this is our critical value, 0.514. That is our critical value, okay? Now, here are the rules for interpreting the R critical. If R observed is less than or equal to R critical, we have to accept the null hypothesis. If R observed is greater than R critical, we reject the null hypothesis. So our value for R observed is 0.71 and for our R critical is 0.514. Therefore, we could say that this one, 0.71, is greater than 0.514. So we reject the null hypothesis and accept our alternative hypothesis, which is this. There is a statistically significant positive correlation between the language aptitude and language learning as measured by the final test in students' first foreign language class. Step 9 is to interpret the findings as a probability statement. Since our alpha is 0.05, we could say that there is a 95% certainty of a statistically significant positive correlation between language aptitude and language learning as measured by the final test in students' first foreign language class. Step 10 is to interpret the meaningfulness of the findings. We have to look for the effect size, and the formula is simply r squared. Our r is 0.71, square it will give you this value, 0.50. This effect size indicates that half, since it's 0.5, half of the variation in performance on the final test, 50% overlaps with or can be predicted by performance on the aptitude test. The rest of the 50% might be related to other performance on the final test or is a mystery in this research. Okay? Final interpretation. We found that there's 95% certainty of a statistically significant correlation between performance on the aptitude test and the summer comes final test with an R of 0.71, a degree of freedom of 13. The effect size, 0.50, can be considered strong. So there you have it, the 10 steps in statistical logic. I hope everything is clear. Again, we use Pearson's R if you want to know the correlation, the strength of the relationship between two variables, okay? Now for another practice problem in using Pearson's R in the 10 steps in statistical logic, we have Marge. Thank you!
After learning the steps on how to compute the Pearson product moment correlation coefficient, let's now try to answer an exercise that will help to better apply what we have learned. The said practice problem can also be found on pages 298 to 299 of Jean Turner's book, Using Statistics in Small-Scale Language Education Research. We will also follow Turner's 10 steps in statistical logic in solving for Pearson's R. Allow me to read the practice problem. A group of researchers are interested in determining whether teachers' perception of the importance of a particular learning strategy is related to the frequency of their use of the strategy. The researchers used a questionnaire to collect data regarding teachers' perception of the importance of the strategy. They had a team of research assistants who did observations of the same teachers to determine how often they use the strategy. The perceived importance scale yields scores between 1 and 5. The frequency of use scale yields scores between 0 and 45. The practice problem aims to solve the strength of the relationship between teachers' perception of a particular learning strategy to the frequency of their use of that strategy. Thus, a correlation statistics in the form of Pearson R should be used. The fabricated data from the randomly selected 16 teachers can be seen in this slide. The first step in statistical logic is to state the hypothesis. For this practice problem, two hypotheses were formulated. The first one is the null hypothesis, and the second one is the alternative hypothesis. The null hypothesis states that there is no statistically significant correlation between teachers' perceived importance of a learning strategy and reported frequency of use. The alternative hypothesis states that there is a statistically significant positive correlation between teachers' perceived importance of a learning strategy and reported frequency of use. The second step is to set the alpha to 0.05. The value was set that way because this is an exploratory problem. The third step is to select the appropriate statistical analysis for the data. In its clearest sense, Pearson R is the most appropriate tool to use because of 4 reasons. Number 1. The strength of the relationship between teachers' perceived importance of a learning strategy and the reported frequency of use is the focal point of this practice problem. Second, teachers were randomly selected as participants, and the methodology chosen was designed to yield normally distributed data. Third, perceived importance of a learning strategy as a variable is distinct from the reported frequency of use. Lastly, to guarantee that the 2 variables relationship is linear, a scattergram was created. For step 4 of the statistical logic, we now proceed to the collection of data. We get to see a glimpse of the data presented a while ago. Step 5. Step 5 aims to verify if the assumptions are met. The first assumption is that the independent and dependent variables must be measured on an interval scale. This assumption was met because the scores obtained by the teachers in terms of perceived importance on a learning strategy and frequency of actual usage of the learning strategy measure things exactly. The second assumption is that the data for each of the 2 variables are normally distributed in the population from which the participants were randomly drawn and in the 2 groups. Just like the first one, this assumption was met because the 2 variables are norm referenced and majority of data points are relatively similar. Third assumption is that each pair of observations is independent. This was met because none of the questionnaire items on teachers' perceived importance of a learning strategy is evident on the observation process of strategy utilization. The fourth assumption is that the relationship between the 2 variables must be linear. This was met because there is a linear relationship between the 2 variables, as you can see from the scattergram. The independent variable found in the x-axis is the perceived importance of teachers in a learning strategy. The reported frequency of usage, the dependent variable, sits within the y-axis. Their corresponding values were plotted to form a scattergram, thus forming a linear relationship and meeting the final assumption. From looking at the scattergram, one can clearly see that the line pattern follows, although not perfect, a moderately positive correlation. Thus, because all of the assumptions were met, Pearson's R is the correct statistical analysis to use. For the actual computation, it is advisable to create a chart to make the process of solving clearer. The labels for the created chart are the following: the participants, the values of x, y, x squared, y squared, and the combined value of x and y. For step 7, we will now calculate the observed value, which is to be compared later on to the critical value. Let us now take a clear look to these values. We can see that there are 16 participants, and the values of X and Y were also plotted in the chart. We also see the squared value of X and Y and the values of the combined X and Y. In the last column, we see the sum of the values of X, Y, X squared, Y squared, and XY amounting to the following. The sum of X is equals to 61.41. The sum of Y is equals to 579. The sum of X squared is equals to 239.03. The sum of Y squared is equals to 21,369. And the sum of XY is equals to 2,258.07. As we all know, we need to compute these values, for they are essential parts for the actual computation of the observed value. This is the formula for Pearson's R. We get the value of R by finding the difference between the products of n and the summation of xy to the summation of x multiplied by the summation of y. Once we get the value of the numerator, we divide it to the value of the denominator. We can compute the value of the denominator by finding the square root of the values of these two brackets. The first bracket is the difference between the product of n multiplied by the summation of x squared to the square of the summation of x. We get the value of the second bracket by subtracting the product of the summation of y squared and n to the square of the summation of y. Once we have multiplied the value of the first bracket and the second bracket, we need to find its square root. Afterwards, we will now divide the numerator to the denominator. The resulting value is the observed value, or R. To calculate the observed value, the next step is to fill in the values from the chart and add the information for n. This can be seen in the current slide. After filling in the values from the chart and adding their information for n, we now continue on with the calculations. 572.73 will be divided to the square root of the product between 53.29 and 6,663. The answer to that is 355,071.27. Now the square root of the aforementioned value, we get 595.88. And then once we divide 572.73 to 595.88, we get the observed value, which is 0.96, indicating a strongly positive relationship. Let us not forget that 0.96 is valuable because this is the R observed, and this will be used in step 8. We now need to determine whether 0.96 is strong enough to be statistically significant. Therefore, we have to follow the remaining steps in statistical logic. Step 7. Step 7 is finding the critical value of the statistic using the degrees of freedom and alpha. For this step, we need to find first the value of the degree of freedom, or DF. The formula for DF is number of pairs minus 2. Therefore, the number of pairs is synonymous with n. Thus, it is 16. 16 minus 2 is equals to 14. That is why the degree of freedom is 14. Alpha is 0.05, as mentioned earlier. Next, for step 3, we need to look at the table of critical values for Pearson's R. You can see in this slide the website in which we can find the table of critical values. To continue, we can see the degree of freedom is 14, and we can see that 0.05 over there at the topmost part, the value is 0.05. When they meet together, we can now state that the critical value is 0.497. We go now to step 8. Step 8 is the comparison of the observed value and the critical value. Here are the rules for interpreting the critical value. If R observed is less than the critical value, we must accept the null hypothesis. If R observed is greater than the critical value, we reject the null hypothesis. If R observed is equals to 0.96 and R critical is equals to 0.497, 0.96 is greater than 0.497. Therefore, it means that the observed value is greater than the critical value. Therefore, we will reject the null hypothesis and accept the alternative hypothesis. Our alternative hypothesis is that there is a statistically significant positive correlation between teachers' perceived importance of a learning strategy and its reported frequency of usage. Step 9 is to interpret the findings as a probability statement. The probability statement is this: there is now a 95% certainty of a statistically significant positive correlation between teachers' perceived importance of a learning strategy and its reported frequency of usage. That's not the end. We still have to follow step 10, and that's to interpret the meaningfulness of the findings. Interpreting the meaningfulness of the findings, it also means that we must find the effect size, which is equivalent to R squared. If our value of R is 0.96, we need to find its square, which is 0.92. Therefore, in the variation of teachers' reported usage frequency of a learning strategy, 92% can be predicted by their perceived importance of the learning strategy. The remaining 8% of what might be related to reported usage frequency is unsystematic and a mystery. And to summarize the statistical logic for this problem, we found that there's a 95% certainty of a statistically significant correlation between teachers' perceived importance on a learning strategy and its reported frequency of usage, with the value of R 0.96, degree of freedom is equals to 14, thus the effect size, or R squared, is equals to 0.92, it can be considered strong. We hope that you have learned a lot in this tutorial, and we hope that you have better understood the parametric Pearson product moment correlation coefficient. Thank you!